Hello all, my name is Santosh and today we'll be seeing about Taylor series and its expansion. So let's start with it. The Taylor series is a polynomial or a function of an infinite sum of terms. Each succession term will have a large exponent or higher degree than the preceding term. So this is the formula of Taylor series where it says f of a plus f dash of a, that is first differentiation of a divided by 1 factorial into x minus a plus f double dash of a, or second differentiation of a divided by 2 factorial into x minus a whole square plus third differentiation divided by 3 factorial into x minus a whole cube. So it goes on like this up to nth differentiation, that is up to the terms that we wanted to differentiate it. So this is what is Taylor series, and the above Taylor series expansion is given for a real value function f of x, where f dash of a, or the first differentiation of a, second differentiation, third differentiation, etc., denotes the derivative of the function at point a. If the value of point a is 0, then the Taylor series is also called as Maclaurin series. So if you take the value of a to be 0, then f of a is also going to be 0, or it might vary. So over here you can call it as a Maclaurin series. And if it's not equal to 0, then you'll get the Taylor series form itself. So the theorem of Taylor series. Assume that if f of x be a real or composite function, which is a differentiable function of a neighborhood number that is also real or composite, the Taylor series describes the following power series. So take f of x equals to f of a into first differentiation of a divided by 1 factorial into x minus a plus second differentiation of a by 2 factorial into x minus a whole square plus third differentiation of a into divided by 3 factorial into x minus a whole cube plus so on. It just goes on up to n factorial of a divided by n factorial into x minus n whole to the power n, x minus a whole to the power n. And this can be given in terms of sigma notations, that is sigma of f of n a divided by n factorial into x minus a whole power n. That is what will be the last term of the series also. And this is the sum of all those terms. And where f of a of n equals to n's derivative of f, and n factorial is the factorial of n. That is how many number of differentiation are doing, that will be the number over here as n, and you'll be taking the factorial over here. Now let's see for the proof for Taylor series. So we know that the power series can be defined as f of x. So here when we say power series, it's nothing but the Taylor series itself, where power series is another name for it. So f of x equals to sigma an a to the base n x n equals to a naught plus a1 x plus a2 x square plus a3 x cube plus so on. So when you take x equals to 0, so f of x equals to a naught. So differentiate the given function, it becomes f dash of x, that is first differentiation of x, which is equals to a1 plus 2a2x plus 3a3x square plus 4a4x cube. So just differentiating all the terms over here, and you get this complete answer over here, where it goes on up to n minus 1 a to the power an x to the power n. So again, when you substitute x equals to 0, we get f dash of 0. That is, when you substitute 0 at the place of x in the whole term, you'll be getting 2a2x and 3a3x square, 4a4x cube. Wherever you have the x term, it will become 0, where you'll remain only with a1. So differentiate it again, we get that is the second differentiation. You'll be getting 2a2 plus 6a3x plus 12a4x square, and it goes on. And again, you substitute 0 in place of x, you'll be getting 2a2. And all the terms that contain x will again become 0. So therefore, second differentiation of x divided by 2 factorial is equal to a2. That's what is given over here. So by generalizing the equation, we get f of nth differentiation divided by n factorial equals to an. So when you substitute all these values in power series or the Taylor series, this is the form that you get, and this is what is called as the Taylor series. Here you can see that. So f of x equals to b plus b1 of x minus a plus b2 of x minus a whole square plus b3 of x minus a whole cube and so on. So now if x equals to a, we get that bn equals to f of a of n factorial divided by n differentiation divided by n factorial. So now substitute bn in a generalized form. That is, we'll just change the values of bn as a over here, or put in all the values of bn over here. So f of x equals to, so when you substitute the value of Bn into the power series, this is what you get, and this is what is called as the Taylor series, and hence we proved it. So now let's see a question relating to Taylor series. So this is the question. Determine the Taylor series at x equals to 0 for f of x equals to ex, e to the power x. So now f of x is e to the power x and x is equals to 0. Now let's first differentiate ex first time, and that will be e to the power x itself. And second differentiation also will be e to the power x. Third differentiation also will be the same thing. Now let's substitute the value of x in all the functions or in all the differentiations, where e to the power 0, that is x will be substituted as 0 everywhere, and it will be e to the power 0 equals to 1. Now when we put this into the Taylor series formula, that is f of x equals to f of 0 plus f dash of 0x plus f double dash or double differentiation of 0 by 2 factorial into x square plus f triple dash of 0 by 3 factorial into x cube plus so on. Over here you can see that in the previous formula we saw that x minus a whole square, x minus a whole cube, where you don't have the a over here because a's value is 0. So if you substitute that, you won't be having a at all. It'll just be x and x square, x cube and so on. And when you substitute all the values for this formula, this is what you get. E to the power x equals to 1 plus x of 1 plus x square, x into 1 plus x square divided by 2 factorial into 1 plus x cube by 3 factorial into 1 plus so on. And when you solve it, it will be e to the power x equals to 1 plus x square by 2 plus x cube by 3 factorial or x cube by 6, and it goes on. And this is all about Taylor series. Thank you.